Yeah, please get started.
Okay. Hi, everyone. Thanks for joining our seminar today. I just want to make a point that we are being recorded and live streamed to YouTube. So if you don't want to be recorded on Zoom, you can exit now and watch the talk on YouTube instead. And if you would like to join again at 1 p.m., we have a social, which is usually very interesting. So I'll just wait for some time before people exit if they want to. So hi, everyone. Thanks for joining our seminar today. We are a group of people who are very excited about Trustworthy ML. And so we started this initiative. It's almost been a year now that we have been growing very strong. A little bit about the initiative. So we have this seminar series, but there are also a lot of other goals and efforts related to our initiative. The first one is to enable easy access to fundamental resources, for which we have a curated list of tutorials, courses, and papers on our website. Please check them out. We also, through this seminar series, we also provide a platform to Rising Star Spotlight Talks and Twitter highlight series, which help our early career researchers to grow. We have an active Twitter handle where there's a lot of discussion and debate, so do join us there. And soon we'll also have a very good event related to Trustworthy ML, so please keep an eye out for that. Talking about today's agenda, we'll have Sanmi's talk from 12 to 12:45 p.m. ET. If you want to ask any questions, please do that using the Zoom Q&A tool. You can also comment and upvote on the questions. From 12:45 to 1 p.m., we'll have a Q&A and moderated chat with Sanmi specifically about his journey into machine learning and his research process. At 1 p.m., we'll have a social. It'll be very informal and sort of like a fun chat with our audience. So please hang around if you'd like. Talking about our speaker today, we have with us Sanmi Koyejo. Sanmi is an assistant professor in the Department of Computer Science at UIUC. He also spends his time, some of his time at Google Brain. His research interests are in trustworthy machine learning. On the applied side, he's into neuroscience and healthcare. Sanmi has been the recipient of several awards, including a Best Paper Award from the Conference on Uncertainty in Artificial Intelligence, a SCIP Alice Early Career Award, Sloan Fellowship, NSF Career Award, and a lot more. He also serves as the president of Black in AI organization. Today, he'll be speaking about towards algorithms for measuring and mitigating ML unfairness. We also have amongst us Gaurush Hiranandani, who is the lead author and also Sanmi's student on a lot of work that he's going to talk about today. So I'll hand it over to Sanmi now.
Thank you very much. Let me share my screen, but also mention Gaurush is a former student, so he's graduated and is now in the workforce. So it's a real pleasure to join you today. Thank you, Chhavi, for the very kind introduction. Today, my goal will be to talk through what I think are some interesting questions at the edge of algorithmic unfairness, particularly from the point of view of group fairness questions. And so I'm hoping I'll cover a lot of material, maybe not that deeply, but I'm hoping that some of the discussion here is a primer for maybe taking a deeper look at some of the papers to get some of the details. So to set things up, I think for this group, I probably don't need to spend a lot of time motivating fairness, but I will mention, as I think would be old hat for many of you, that we're now much more aware of many of the issues that machine learning models can have when we train and deploy them. I think for quite a while, the general dominating wisdom was that because we were using data, you automatically had great, unbiased, and sort of objective ways of thinking about your problem. I think now we know that algorithms take on many of the biases that we have, either from the data collection or the algorithm construction, evaluation, many parts towards the pipeline. There are lots of great examples of this issue in the literature, but to ground things a bit, I'll mention the Gender Shades project that many of you might be familiar with, which was looking at existing work, trying to predict gender from faces, and looking at how it behaved across different demographic subgroups, and finding much worse performance, the main finding from this paper, much worse performance for darker females compared to lighter males, as an example. Now, the task of trying to reduce unfairness properties in ML is necessarily a complex, broad, rich one. I don't think, I'm sure I won't do it justice. I think it's hard to do it, to sort of cover everything in detail in one talk. Here I'm showing a pipeline, which I think is a good one for thinking about various aspects of where we should be thinking of interventions around fairness for a machine learning pipeline. This particular paper from Chen et al. Is targeted at healthcare, but I think it's a good proxy for thinking about many machine learning life cycles. And so the way that they reason about the problem is that some of the cases or some of the instances where unfairness issues can occur can start all the way from how we choose to select problems. And their argument is that in problem selection, we should try to take care to build in stakeholder needs. And sometimes even ask the question, should we be using machine learning for this task at all? And I think that's an important aspect of thinking about deploying or potentially deploying machine learning systems. The next step in this pipeline is data collection. And again, this is one of the cases, the instances where we can, if you like, break the system. And the way that this can break is systematic undersampling, for instance, of different subpopulations, other kinds of bias and confounders in how we collect data. The next step that they outline is defining what outcome you want. And I'm going to think of this in a narrowish sense and think of this in terms of some kind of measure of performance. And so how do we measure performance and particularly sort of instantiate this in a way that we can actually deploy or use in deployments of machine learning systems. The next step is algorithm development, which is where I think most of machine learning is most comfortable. And then finally, after you deploy your system, what is it doing in the real world? Both to catch issues that you might have missed, but also to ensure good performance, good generalization, potentially new issues with unfairness, again, that you might have missed in the beginning. As mentioned a few minutes ago, this is a very broad outline and a broad set of topics with lots of great literature with great people across disciplines. In my talk, based on my both interests and the work that we've done, I'm mostly going to focus on a fairly small subset of these. I'll talk a bit about questions in outcome definition, and I'll talk about some of our recent work in algorithm development. So as mentioned, I'll have three broad sections. On the outcome or metric selection question, I'll talk about some work we've been doing on metric elicitation, specifically thinking about how to select group fairness metrics based on interactions with stakeholders. Next, I'll talk about some mitigation work where we've been looking at intersectionality. So what changes and how do you implement fair and unfairness mitigation strategies when you have, for instance, overlapping groups? And then finally, I'll talk about issues with missing features. Here, I will focus on settings where we're interested in mitigating unfairness, but we don't have group information in the training data. I'll talk about a somewhat specialized setting here where, while we don't have this information in the training data, we have there is some way to query an oracle to get a measure of the performance of the system and ask the question, can we still construct methods that improve or mitigate unfairness issues? Okay, so a bit of background to get things started. So as many of you know, one of the main machine learning tasks is classification. And here I'm showing the specific example of binary classification. And I'm showing this because thinking about classification statistics will be the basis of a lot of the discussion I'm going to have today. So if you build a machine learning classifier, a binary classifier, you generally are asking a classifier to make a prediction of yes or no, in this case indicated by 1 or 0. And your measurement is benchmarking that against the ground truth, where the ground truth is itself 1 or 0. And for such a system, you can easily pull out 4 statistics. The true positives, which is a fraction of examples where the prediction of the model matches the ground truth and they both predict positive. True negatives, for the sort of opposites, they match each other, but they both predict negative. And then different kinds of errors, false negative and false positive errors. And one observation, which will prove useful as we move forward, is that many of the ways that we have constructed to evaluate machine learning metrics can easily be developed or can easily be described in terms of nested functions of the confusion matrix. So some of these you might already be quite familiar with, all kinds of weighted accuracy. You can write in a straightforward way as a function of the confusion matrix, but also measures like precision and recall can be written in terms of ratios of confusion matrix entities. Beyond that, of course, you can increase the complexity as much as you like. So I'm showing here, for instance, maybe the most popular in this page, something like F-beta measure, popular in information retrieval, which again can be written as this ratio function of confusion matrices. And what I'm hoping that you take away is not to read all of these definitions, but the main takeaway, hopefully, is that most measures for classification performance can be described in this way. And I'm highlighting this because the confusion matrix will play a central role in a lot of the work that I'll describe in the next few minutes. Okay, so I've described general classification metrics. What about group fairness or fairness broadly? So as mentioned, this talk will focus entirely on group fairness questions. The idea here is that I have different subgroups, each containing a subset of individuals. And my notion of fairness is that my classifier should have similar behavior across different subgroups. Now, to formalize this idea, typically you need some measure of what similar behavior is. And so there's a variety of work reasoning through what different kind choices of measures or metrics that you want to equalize across groups. The most common is to ask that your model have equal accuracy across different groups, but you could also have equality of opportunity and statistical parity, a variety of other measures. Again, all built around this idea of similar behavior across groups. Beyond this work, or in addition to this work, I want to highlight that many of these metrics, again, can be thought of as computing a confusion matrix, and then asking for some feature or some function of the confusion matrix be equalized across groups. Of course, this idea, I've argued, is quite general, and many ways that exist in literature already of thinking about fairness, particularly for binary classification or classification problems broadly, again, can be written in this broad framework. One issue that comes up, and I've alluded to this a little bit through my discussion, is that in general, you can't exchange classification metrics for each other. So in general, optimizing for one metric doesn't necessarily mean that you are doing the ideal job, if you like, for a different metric. And I'll give a concrete example of this, but I think now it's well known that sometimes called impossibility results in fairness, where showing that given 2 or 3 different kinds of measures, it's easy to show that you can't optimize all of them simultaneously. You have to pick which measures you're interested in optimizing. This, of course, brings up the question of what statistics or what measures should one be looking to equalize across different groups. To ground this discussion a bit, I'll mention again something that I expect is familiar to this audience. Work out of ProPublica on machine bias. Here, ProPublica looked at existing work on recidivism prediction by Northpoint, where Northpoint had evaluated fairness using calibration measures, whereas ProPublica looked at false negative and false positive rates and showed that the behavior, even though the behavior looked quite good in terms of calibration, the models looked much, much worse when viewed through the lens of false positive and false negative rates. So again, this is motivation for thinking about how to select metrics. And I'll talk now about metric elicitation as a framework for trying to formalize this idea for various kinds of problems, specifically focusing on classification problems for now. So the idea of metric elicitation is that I want to select a metric by querying stakeholders and using their feedback to quantify the utility or the measure of performance of a model in this case. The way you do this is that you, given some data, some context or data distribution, I'm going to create some kind of black box system, and I'll open the box in a few minutes, but I'll create some system that generates a sequence of queries. These queries are posed to the user or a set of users. And based on their results, each of these results being preferences, we want to very quickly nail down a good approximation of the notion of performance. So I'll go through both empirical and sort of conceptual examples in a little bit of detail for eliciting linear binary classification metrics. And then I'll talk about the results for more complex settings and maybe leave the details of that analysis to papers and offline discussion. So as mentioned at the beginning, linear metrics for binary classification are relatively simple. You should think about this as different kinds of errors that a model makes, which can be false positive and false negative errors. And I want to figure out a weight for false positive relative to false negative. The idea being one of these kinds of errors might be more costly, and I want to assign a relative cost for one of the errors versus the other. And so the goal of this linear binary classification elicitation problem is to figure out the values of A1 and A2. Without loss of generality, and we'll come to this in a little bit, observe that only the relative value matters. So scaling the measure or ranking of how good a model is invariant to the actual value. What matters is sort of the relative value of A1 and A2. So if you like, the ratio of A1 and A2. So I'll start off with sort of what this might look like in practice based on ongoing work. So this is a bit early, but ongoing work we've been doing with some colleagues on trying to evaluate practical metric elicitation. So on the right-hand side, I'm showing what a UI might look like, a user interface. So the user comes in, they're given a pair of sort of model performance summaries. And in this example, we use two kinds of summaries. We use the sort of bar chart kind of summary, and then we use this sort of arrow chart kind of summary. The underlying problem or the underlying elicitation problem that we're looking to address is asking users for a metric for a diagnosis problem related to cancer as an illustrative example. And so there are two phases in this task. There's an elicitation phase where we show the set of users pairs of these examples. And I'll talk about how we choose what pairs to show. And the goal here is to show pairs in such a way that we can nail down a good approximation for their preferences as quickly as we can, meaning the fewest number of queries. And once we're done with the elicitation phase, we now have an evaluation phase where we create a bunch of new queries. And now we have a measure of what we expect the user to pick as a better or worse performing model based on our approximation of their preferences. And so in the evaluation phase, we're observing users' preferences and evaluating or checking how often user preferences match the preferences that we expect based on our elicitation procedure. So again, early work, but a few results where we've shown that the elicitation procedure is much more accurate in matching user preferences in terms of correctly predicting their future preferences compared to using a default measure like accuracy of the classifier. And again, this is a case where we expect asymmetry between the different kinds of mistakes. We expect that, again, this is a diagnosis situation. We expect much more weight on true positives versus true negatives. Behind the scenes, the way that this approach works is that instead of looking at the models themselves, we look at the space of confusion matrices, as I outlined a few slides ago. And the idea is, given a model and a model class and a data generating distribution or a data set, I can map out the feasible space of sort of all possible confusion statistics that can actually be achieved by sort of any model in this class. So this is interesting because you can actually show that you can get a full characterization of sort of all feasible possible performance behaviors of a particular model. Of course, doing this explicitly can be computationally expensive. Here we'll mostly exploit the fact that knowledge of this property and then try to efficiently just use parts of the feasible space that are most useful for a particular application. At the main takeaway I'd like for you to have from this slide is, if you characterize for binary classification this feasible space of confusion statistics, it has this nice convex shape. So it's a compact convex set, and it's closely related to the RLC curve if you're familiar with RLC curves. And in fact, weighted metrics of the style of cost for false positive versus cost for false negatives look like linear functions in this space. And we know from sort of basic optimization and linear algebra that if I am trying to optimize some linear function subject to some convex constraint, the optimal is going to lie somewhere on the boundary. What is really helpful and useful about this is that now we know that we can characterize metrics in terms of sort of points along the boundary of feasible confusion matrices. And so the way that we use this in the elicitation procedure is that instead of searching for a metric, again, the metric in this setting is this linear function. The way that we search for the metric is we can just focus entirely on the boundary, which is, again, by virtue of this relationship between linear metrics and the boundary, we can just focus only along the boundary. This means that the problem goes from originally over metrics over classifiers, which is a high dimensional and sort of possibly infeasible space, to metrics over confusion matrices, where for binary classification, this is a 4-dimensional space. By exploiting degrees of freedom, we can reduce that 4 dimensions to 2 dimensions. Here I'm showing true positives and true negatives. Equally, any 2 values are equivalent. So I could also show false positives and false negatives, and it's the equivalent characterization. And then finally, I've exploited the fact that all linear metrics can be identified based on some point in the boundary of the feasible space, and which means that instead of a 2-dimensional search, I only need search on 1 dimension. So I only need to look on the boundary for the point that matches the behavior closest to what the oracle stakeholders are interested in. And this gives me my metric. So to actually implement this, the way that we do this is that we unroll this 1-dimensional space. The thing that we know the x-axis, so we know the unrolling procedure based on angles. We don't get to see this function in any kind of, so we don't know the metric yet. That's what we're looking to learn. However, we're able to query for pairs of points along the boundary binary preferences from the stakeholders. So specifically, an example might look like this. I've broken up this line into 5 points where I can ask, do you prefer model B versus model A, C versus B, D versus C, E versus D? So these are the sequence of queries I might ask. Once I'm done with these sequence of queries, in this cartoon example, the results are better, 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 worse. And once I have those results, I know that wherever the optimal, the peak of this function is, it must lie somewhere between theta C and theta E. And so I can reparameterize my space and just look at theta C to theta E and then repeat this procedure again. So this looks, if you're familiar, like a binary search problem. In fact, you can show that this is just an instantiation of binary search. And so to summarize the key idea here, we can show that this binary search-based elicitation procedure can provably recover the oracle metric when the metric is linear. And it's guaranteed to have good accuracy properties. In particular, since we're most sensitive to how many queries we ask, we can bound the number of queries we need to accurately elicit the weights A1 and A2. Of course, we've extended this work quite a bit. We've looked at adding system noise and ensuring that the procedure remains robust to some kinds of noise. And I think expanding beyond the noise models we've looked at so far is an interesting open problem. And then we looked at beyond binary classification to multi-class classification and other more complex metric families, like ratio families, polynomial families, and the like. This idea becomes the baseline or the sort of underlying key idea for a more complicated problem of eliciting group fairness metrics. Here, to make the problem, I've made the problem a little bit more general on purpose. So instead of just a binary classifier, I'll consider a K class classifier. So there are K classes and M groups. And in this setting, we chose a fairness violation measure that looks at the discrepancy between all pairs of groups. So it's an absolute value difference between some statistic measure from the classifier between group U and group V in this example. So based on this discrepancy measure and what I already outlined as the sort of performance measure, our class of functions over which we are looking to elicit has 3 terms. The first term is the overall utility, and here we're just focusing on linear. So think about this as weighted accuracy as outlined before. The second term is a weighted measure of discrepancy between groups. So we have a weight for every pair of groups and summed over all the groups. So this is sort of weighted fairness violation. And here the goal would be to estimate what these weights would be, the best match behavior that we want the model to have. And then the third term here is a trade-off, which trades off between the utility term and the fairness violation term. So because of time and sort of the breadth of things that I'm covering today, I won't go into detail, but I'll mention maybe just the key steps here. So we can show, and we showed in recent work, that you can elicit first the utility part of this class of metrics using K-squared queries. This is important or interesting because the degrees of freedom, number of entries in A, remember there's an A for every kind of mistake that the model can make. And if you have a K-class problem, there are K-squared entries in the confusion matrix. And so this is essentially the degrees of freedom in A match the query complexity. Next, we can show that you can use the estimated A to elicit the fairness violation weights. Again, there are K-squared times M choose 2 for every pair of groups. We have K-squared kinds of fairness violations. And then we have M choose 2, which covers sort of every pair. So this again matches the degrees of freedom in the problem. And finally, we can elicit the trade-off term, which is just a number between 0 and 1, and it takes order 1 queries. The key takeaway I mostly want to highlight here on the sort of technical side is in this work, where the main results maybe that we've shown, in addition to query complexity characterization, is that the query complexity roughly scales with the degrees of freedom in the problem, which we conjecture is the optimal scaling for these kinds of problems. So we don't think you can do any faster. Okay, so I'll switch gears now and talk about more mitigation questions in fairness from elicitation. So now you have your metric, and now you're looking to deploy this to improve the way your model behaves in various settings. And here I'm going to talk about a specific class of problems that have been highlighted relatively recently, where one can have overlapping groups and you want to still mitigate unfairness problems. So a lot of the motivation for this line of work comes from work from Kearns et al. And what they showed is that if I have a set of individuals and say there are two sort of classes of demographic features, or sensitive attributes. In this example on the right, I'm showing old, young, black, white, where subsets of individuals fit into, or you can classify into one of these four categories. And what they showed is that if you have an adversarial classifier, there are ways to construct the classifiers such that if I look separately at each of the dimensions, it looks like I have a good sort of balance or if you like, fairness between the sub-entities or the subgroups. However, if I look at the intersections, I can see that the model has behaved quite badly. So what this means, for example, is that if I look, in this example here, if I look at the behavior of the model for old versus young, I could see that the results are close to equal. If I look at the model for black versus white in this example, the results look close to equal. However, if I look at the intersections, if I look at A, B, C, D separately, there are ways to construct classifiers that have good behavior at the sort of meta group level, looked at separately, but have very bad behavior when looked at in intersections. And so one of the ways that they coined this term fairness gerrymandering, which is illustrative of this issue of sort of the way the classifier or adversarial classifiers can induce this behavior. And then they constructed more complicated notions of groups, which I'll talk through for a couple of minutes. So again, here we're looking at fairness mitigation with multiple subgroups. Here I'm showing different ways that you could imagine grouping your data or grouping your individuals based on sensitive attributes. So in this setting, we have what we call independent groups. So female, male, old, young, black, white, which is essentially across every dimension. We just sort of sum things. There are also intersectional groups, which is each one of these boxes separately. And then what motivated or inspired by the Kearns et al. Paper, what we're calling gerrymandering groups, which are essentially all subsets. So it's a group of all subgroups, which again can get quite big. So if you look through, you can see that this is extensive. So it sort of looks at all combinations of subgroups. And so the question is, we already know how to build classifiers that do well for independence groups. Most of the existing literature, I apologize. Most of the existing literature, if I have no overlap between groups, there are good models already to handle that. And the Kearns et al. Paper suggested an approach that can work for what they call gerrymandering groups. And even though they alluded to independent groups, and this is one of the sort of common methods used in the literature, again, the independent groups have this potential issue where you have good behavior at the group level, but you have a risk of bad behavior at the sort of intersectional group level. So to address this question, we sort of took a general view where you can think about this as optimizing, again, some utility subject to constraints on the behavior of the model. Again, we're thinking of utility or loss as just a weighted accuracy. This can be relaxed a bit more, but for the purposes of this talk, I'll just maybe allude to the fact that we can have more complicated utility functions, but focus on accuracy because it captures many of the instances people are interested in practice. Here we use a fairness violation, which measures the population behavior versus each group's behavior. So the idea is how close is some statistic of each group to the average over the whole population. So this is related but distinct to sort of looking at all pairs. Here we're looking at each individual subgroup to the entire population as our notion of fairness violation. And this, again, is also a quite general framework. It covers many of the existing kinds of metrics, so you can get back demographic parity and sort of EO type metrics from the setup by picking the weights appropriately. The setting is also intentionally generalized to allow for multi-class classification and also generalized in terms of group definition. So here, this framework allows for sort of arbitrary, potentially overlapping groups. And the question that we were looking to answer is, how do we construct classifiers, mostly focusing on the setting when this group is complex, such that it does well respect to the original objective, which is optimize utility subject to some cost on fairness violations. So lots of details in the paper. I'll give a quick one slide summary. So here we exploit, just like in previous, the first work on elicitation. Here we once again exploit convexity of the metric from the point of view of confusion matrices. And so because of that convexity, we can use standard tools from sort of convex optimization as a way to address this problem, where when we're applying the convex optimization tools, we're looking at the problem purely from the point of view of confusion matrices. Then under the hood, the learners are estimated using some kind of weighted classification model. So in particular, in this setting, we use a primal dual update where you fix the sort of regularization constant and you update the model or the confusion matrix, which is equivalent in this setting to the classifier H. And then you fix the classifier and then you update the sort of the dual variable and alternate till convergence. So I think the key interesting thing, that one thing to pull out from this work is that we show that if I fix these Lagrange multipliers and I'm looking to optimize the classifier, this classification optimization problem you can solve as a weighted classification problem, where you have a weight for every instance, which combines aspect of the utility and then sort of the fairness violation measures. And the key thing that couples everything is sort of this quantity here, which is a measure of summing over all groups that a particular instance is associated with. And so this is an indicator function. So this is 1 if this sample is within the group, 0 if it's not within the group, and then normalized appropriately. And so this gives you a sort of general characterization of what good models that optimize the previous loss function look like with a fixed Lagrange multiplier. So I'll defer to the paper for details of the implementation and also some of the analysis. I will mention, two interesting things to mention. One is that this weight characterization can be implemented both in what is known as an in-processing mode, meaning I'm optimizing my fairness properties at the same time as I'm constructing my classifier. So this is like a joint optimization. And this exact same characterization can also be used in what is known as a post-processing mode, where I learn a probability model first, or I have a classifier existing first. And then my goal is just to find a way to reweight the classifier prediction such that it has better fairness properties. And what is interesting is that the same framework applies to both, where in both settings, you just implement and apply instance weights as necessary. The other key takeaway is that what we found, and this may not be surprising, but I think it's much clearer now, at least from our point of view, after the analysis, is that the behavior of the model and sort of how accurate you can be tends to be very sensitive to the number of instances in the smallest group, particularly when you're working with intersectional subgroups. So of course, this maybe is not surprising after the fact, because again, you're measuring how a particular subgroup behaves, so what the accuracy and other sort of confusion statistics look like for a particular intersectional subgroup. And if you have very few instances, which tends to be common, then this measure of performance for that small intersection subgroup is very noisy, and this noisiness ends up affecting the rest of the algorithm. And so an interesting open problem is to think of maybe additional assumptions, additional constraints that allow us to have better behavior for small intersectional subgroups while still having sort of good modeling and good performance across the entire model. I highlight this, of course, because in practice, sort of a key marker of issues of fairness are that, again, sort of marginalized subgroups tend to be marginalized because they're undersampled. And so by definition, almost, or at least by observation, they tend to have the smallest number of samples in terms of like a number of data samples that have been collected from the certain subgroup. And again, while this is maybe a real world observation, this has consequences for how accurate we expect to be when constructing models that try to address overlapping groups. At the time we did this work, there weren't really any baselines, but for most of these, so I'm just sort of showing various kinds of instantiations of the model compared to each other. The weighted ERM is a sort of in-processing version of the model. The plugin is a post-processing version where I take a learned model and I adjust the weights or the thresholds to get different behavior. And all of these curves show sort of fairness error trade-offs. So you want to be have low fairness violation and low error, and that's the ideal behavior. And we sort of just look at how different instantiations of this model behave on a variety of existing data sets that are typically used for fairness evaluation. And then we also looked at the gerrymandering notion of fairness, comparing, in this case, there's a baseline of the Kearns et al. Approach to the approach that we propose in this paper, showing similar behavior, though behind the scenes, particularly if you use the plug-in sort of post-processing approach, it's significantly, often orders of magnitude faster, while still getting good behavior, good performance. Okay, so I'll switch over to the last line of work, and I think it's pretty quick. The question here is, how do I address unfairness when I don't have group labels in my training data sets? So the way that we view this problem is to think of this as a special case of black box performance metric optimization. So the idea behind the scenes, the expectation is that while the model doesn't actually have any of the sensitive group labels in training, it can ask, whenever it constructs a classifier, so construct a classifier H, you can evaluate the performance and fairness of that classifier based on some black box oracle, which returns back some measure of what the model is doing. And so the question is, if I have this framework, what can I do? How can I actually use this sort of query access to performance and fairness evaluation to build models when I don't have sensitive attribute labels in training? So to outline what we do, I'll take a slight step back and talk about Frank Wolf as an optimization strategy. So some of you might be familiar with this. It turns out to be useful and relevant for this task. So Frank Wolf is a sort of general algorithm for convex problems with constrained convex problems. And the key idea is behind it and how it works is that at every step, it linearizes the optimization problem using the gradients. And then based on this linearized problem, once you solve this linearized problem, you can get an update and you can then sort of update your parameter, linearize at the new point and go over and over again. So I start from some point in my input space, linearize around it. It takes me to this point, linearize around it, and sort of go forward till you get to the optimum. And here, once again, we're looking at the problem from the point of view of the confusion matrices. And so linearization here is, again, looking at the gradient with respect to the confusion matrices and looking or working through the extent to which we can use this algorithm for trying to learn complex classifiers. I should probably mention that the idea of Frank Wolf for sort of optimizing complex metrics exists, and there's some good literature on how to do this already. References on the slide. So in our instance, the issue that we have to deal with is that we don't have access we don't know the metric because we don't have access to the fairness metric. We can only get point-wise query access to it. So we can, given a classifier, we can get a measure of how good or bad it is, but we have no way of knowing an actual value, and there's no way to actually compute a gradient directly. So I'll talk a bit about how we address this first question of how do we estimate this linearization, this gradient, when we don't know the metric, this black box optimization strategy. And then I'll defer discussion of complicated metric families to the reading the paper and just talk about the first part. So how do we estimate this gradient without knowing the metric? So we use a relatively simple idea of sort of local perturbation. So given a certain iterate, what I can do is have sort of epsilon perturbation towards two naive classifiers. So these are classifiers that predict always positive and always negative, which give me sort of these two edges. And based on the results of querying these two classifiers, you can show that you get a linear system of equations with sort of two unknowns and sort of two queries. H1, H2 are the two queries. How good is H1? How good is H2? And the two unknowns are the two weights that constitute the gradient of the metric for this binary classification problem. And you can solve this fairly easily, and based on the solution, you can pull out the gradient at the current iterate. And so using this idea becomes the sort of core of a broader algorithm trying to optimize, again, complex black box metrics using Frank Wolf, as outlined briefly earlier. So at every iteration, we construct a linearized objective. To construct a linearized objective, we need the gradient. To get the gradient, we use this perturbation that I just described. If I have a linear metric, it turns out that the optimal classifier is very, very simple. In fact, we've used this for all of the applications we've discussed so far, elicitation, overlapping groups, and all that, all use the same idea. So weighted classifiers are easy to optimize, either directly or via post-processing. And then I pull out the weighted classifier from the current iterates, and I combine it with my previous iterates in the sort of Frank-Wolf procedure. This is using convex combinations of classifiers, and repeat this till convergence. And so this is the sort of broad framework under which we can try to optimize black box metrics. And again, the key thing is we just only using query access, we can actually construct the entire procedure. What will happen under the hood for more complex metrics, we'll end up with a weight for every instance as the weighted classification problem we need to solve. And again, we have straightforward ways of solving those problems. Pushing a bunch of details, again, for you to look at offline. We looked in the paper at a variety of applications, and I'll encourage you to look for instance, instances of distribution shift and other kinds of issues that we looked at. Here, I'm just going to show our results for optimizing an unknown group-wise error measure. So I don't have demographic information, so I can't compute this error, but some Oracle has validation data. I can use this to compute this error. We did this on the adult data set, and only the validation and test data have the sensitive group information. What we're showing is that the model outperforms all the other baselines, and so behind the scenes, it's also quite a bit faster than most of the other approaches for trying to address this problem. Okay, so I'm about done. I've talked about 3 ideas today, all around improving how we try to address algorithmic unfairness. Specifically thinking about group fairness, I've talked about metric elicitation, which is this task of selecting a group fairness metric based on interactions with stakeholders. I've talked about how one implements mitigation when you have intersectionality and overlapping groups. And I talked about an instance of mitigation when you don't get to see the group information, and during training only get to see it at evaluation time. Of course, lots of open questions, which I'm happy to discuss offline. I guess I want to encourage others to take a maybe look at some of the details of these papers, and sort of mention a general pitch that I think selecting and better optimizing metrics can help us implement more trustworthy ML broadly. Thank you.
Thank you, Sanmi. It was a great talk. I feel like your first idea of using queries to get the preferred metric, and that any metric can be specified in terms of classification matrix is like, confusion matrix is like very unique. As like coming to questions, it was a bit unclear to me, maybe because I lost focus in the last part. Like, how do you deal with the fact that you don't have sensitive features? Maybe you can just summarize.